Good morning, everybody. Welcome back. I know you didn't miss me, but I missed you. I hope your spring break went at least okay, if not fantastic, right? It's always good. Usually what I hear is, well, Mr. Balogh, I slept, or I worked, right, or something like that. Sometimes normalcy is good. This is the last hurrah, isn't it? This is the final unit, right? Keep going, right? You've got 3 more chapters to do, and then it'll be over, right? So keep your heads up, keep going, keep pushing. You can do this. I know it's terrible, right? We've got like this 18-week semester, and it just feels so long. And a lot of you are going to transfer to places that have quarters that are going to feel really fast at first. But hang on for the ride. So tomorrow, right, we've got the exam autopsy. So I was going to say look forward to that, but maybe those weren't the words I should pick. This week is chapter 12. Next week is chapter 13, sort of. It might take 3 days. And then the week after that's chapter 14. And then we have our exam week, and that's it. So just to be clear, do you have a final in this class? Like during finals week, are you taking an exam? No. What are you doing during finals week in this class? The autopsy, right? So we're going to take the 4th exam, the last exam. I don't want to use the word final exam, even though it would be totally appropriate, right? But like we're going to take our 4th exam the week before finals week, and then during finals week, you are going to come to this room on our assigned day for lecture only, right? We'll talk about this later, right? But we're not going to meet in the lab room for the exam autopsy. We're going to meet in here, which is weird, but that's the way we have to do it. All right. Chapter 12. Okay, so for those of you engineers that have to take statics, this is for you. This is the preparation. For the rest of you, you can be very happy that you don't have to take statics, okay? For reasons that you're about to see. And I can teach you basically all of statics in about 30 seconds. You can take a whole semester on it, right? But pretty much I can do the whole thing in 30 seconds. And I will show you why in just a second, or how I will do that. What do you definitely not want to have happen to this bridge? Collapse. Okay, I want you to be very careful about what you mean by collapse. What must be true at all times about the total sum of forces on this bridge? What do you want the net force on this bridge to be always? 0. And why do you want it to be 0? Because if it's not 0, what does that mean the bridge is going to be doing? Be more precise. It's going to be accelerating, right? And do we want our bridges to accelerate? No. Okay. There's another very important concept related to the one we just talked about. We just talked about Newton's second law, didn't we? Right? And it's related, but it's the rotational version. What do you want the sum of torques to be on this bridge? 0. Because if they're not 0, what does that mean the bridge is doing? It's going to start rotating, right? It's going to have alpha, which isn't the motion, it's the change in motion, right? So we want to establish this bridge such that the net force on it is 0 and the net torque on it is 0. Here's a picture. We'll go from coast to coast here, right? Here's a picture of Manhattan, New York, okay? What do we want the sum of forces to be on all of these buildings always? 0. Because if not, the building is accelerating. And an accelerating building is a bad day. What do we want the sum of torques to be on these buildings? 0, right? Because we don't want these buildings to start to rotate, right? So there you go. I did it. Static equilibrium means all of the forces are going to add up to 0, and all of the torques are going to add up to 0, and I'm done. Have a good day. I'll see you in a week. Okay, you know by now in this class it can't be that easy, right? But, I mean, how bad could it get, Mr. Balogh? So we did dynamics in chapters 5 and 6, and again in chapters 10 and 11, where dynamics means that there is acceleration. There could be changes in the motion of an object. More strictly speaking, for engineers, dynamics also means that something is moving. Okay? In physics, can you have a sum of forces on an object be 0 and still have the object moving? No. Yes. Name an example of where the net forces are 0 and the object is still moving. We've done this one before. Cruise control on your car. What's the job of cruise control? To maintain the same velocity, which means the acceleration is 0. Can your car be moving? Yeah. Yes. And if it's not accelerating, it's not changing direction or speeding up or slowing down, that means it can be moving and have a net force of 0. So I'm going to speak the way engineers speak, because engineers they break physics all the time. It's okay. It works. Engineers consider statics to be the not moving, not accelerating case. Dynamics is motion and change in motion, right? That's how they define it. So I might slip up every once in a while. So correct me if I get away from the engineering definition. But this can't be so bad, right? Back in the day, we had all those accelerations to deal with, and our connected objects, and our inclined planes, and our pulleys, and all that kind of stuff, right? It can't be so bad, because now, we don't have an acceleration to worry about, right? The acceleration caused all kinds of problems with choosing an axis direction and all that kind of stuff. So how bad can this get? I will apologize in advance for the profound trauma you are going to experience whenever you look at a ladder after Thursday. All right, so you'll see what I mean there. Okay, but how bad can it be? So I've taught you all the physics and engineering, right? From here on out, it's examples, right? Showing you the applications of these principles. And what we've got to do is we've got to apply, add up all the forces equal to 0, add up all the torques equal to 0, and then figure out what it is that they want us to solve for. Part of the problem of every word problem we've ever had in this class, right, is how do I know if I am drawing the picture right? So what I want you to do is just a little bit of practice right now together with the people near you. Start drawing this picture and then let them see what you're doing while you're doing it, right? Compare and contrast. Oh, is that what this means? Or I don't sure what I'm supposed to see here. I want you to take a stab at it. I, on purpose, haven't put the picture up, okay? So go ahead, take a stab at it here for a couple minutes and help each other out, compare and contrast, see if you are getting the same thing. Have you compared pictures yet? Some of you I should have told to do it in pencil. Oh well. All right. Okay. There are lots of objects in this problem. Name one of them. There's a sign. There's a beam. There's a wire. And there's a wall. Right? Did we get anything else? No, look, it looks like we got it. Yeah, okay. So if I start off by saying, okay, like, here's a wall, right? Walls normally are vertical. Check in. How was your spring break? Were some walls tilted now? Okay. I like to kind of, I don't know, indicate that maybe that's some way like a solid or something. You can shade it. You can do a bunch of different things. I can use all the colors on my iPad, but I like to kind of replicate what you have to do with a pencil. Okay. So now there's a beam, right? And there's something very specific they tell us about this beam. Yeah, but it's a horizontal beam. I really only have 2 examples to do today. I will cover all static problems with 2 examples. So I'm going to, now, it doesn't really say, so I brought the meter stick just to sort of demonstrate this, right? So here's my beam, right? Okay, and we know it needs to be horizontal, right? And we know the problem tells us that there's like a wire that's attached to one end, right? And this wire goes from, does it say where on the beam? Support a wire attached to the wall. It doesn't, okay? We know that there's like a sign that's being hung off the end of this beam, right? And there's a wire, and it doesn't really say where, okay? So we'll get to that in a second. But I can't, like, where's the wall come into play? Like, how would I put this beam if I wanted to run like a string or a wire? Go over here, okay? So here's my wall, right? And I want to support this beam, right? And I'm probably going to stick out from the wall, right? Is it going to like float away from the wall? No, because what's this end going to do? It's going to fall, right? So like, I feel like it needs to be sort of like attached to the wall somehow over here. It doesn't really say, right? And then my wire is going to come off somewhere, right? Okay. So this is kind of the picture I'm getting in my head. I've got a horizontal beam. There's a sign coming off one end, and there's like a wire that's coming up. I don't know if maybe you've ever seen like a store sign or something like that. It kind of looks like that. That's kind of the idea I'm getting in my head. So we'll go ahead and draw my beam. Okay, something like that. Now this wire, okay, is supported by a wire attached to the wall. So I know the wire has to be attached over here somewhere, right? The question is, where does the wire go? Now, because I wrote the problem, I'm not very good at writing. I should have said that the wire was attached to the far end of the beam at the location where the sign is hanging off. Yeah. It does. What I didn't tell you is that we're trying to like minimize the tension or make it so that the tension is most effective in this problem. Like as a civil engineer designing a structure where maybe you have to support this sign, you want to design in such a way that you take advantage of the forces you have in the problem. You also have design constraints sometimes. So if we take this wire and say attach it closer to the wall, like if we do a situation where maybe we attach it here and go up like that, which I saw some of you drawing, which I don't fault you for because it wasn't clear in the problem, right? It's entirely my fault. If this wire in red, I would have more tension in this wire to hold up the beam, okay? It just would take more force in that wire. We want to kind of sort of minimize all the forces in our design here because, I mean, there are limits to what wires can do, right? Like the amount of tension, and they're going to snap, okay? And you want to design around those limitations. What's the sign say? No. You do not. Okay, two things. If you ever see my name on a ballot anywhere, please come find me and kill me because somebody is exerting an influence over me that I don't want. Okay? Number two, you do not want me in this elected official. I promise you. Okay? First executive order. Sweats are allowed everywhere. Okay? Marriages, funerals, the workplace, sweats are now the de facto standard for all clothing. Sweatpants and t-shirts. Number two, SUVs are illegal. I don't understand the concept of a sport utility vehicle. I just don't. Okay? Yes? Okay. Trucks, to some extent, are okay. Okay? But an SUV, I don't understand. It's neither sporty, nor does it have any utility. It's a vehicle, I'll grant you that, right? But they're too small. Some of them are too small. Oh, a lot of them. Yeah, and this is the small ones that I don't get. I'm a favorite. I do like small cars, okay? The problem with small cars in America is that nobody drives them, and so if you drive the small car, you're dead, right? Anything else hits you in America. Anyway, but you go to Europe where they all got small cars everywhere. It's fantastic, right? Everybody's got a small car. You got parking for days. It's fantastic. All right. And trucks. Oh my gosh. I will outlaw trucks that are not being used as trucks. I think is it an oxymoron to put leather upholstery in a truck. Okay? And if the truck is not carrying a bunch of tools or supplies, why are you driving a truck?
Is this apply to the Cybertruck?
Yes! It's an abomination on many levels. I'm a big fan of electric vehicles, but the Cybertruck, oh my gosh. Don't understand why things exist. I'm sorry, this was a tangent. Doesn't matter what's on the sign. In fact, I'm just going to draw this sign. I broke a rule, right? This is supposed to be simple. I got distracted, right? There's just going to be something attached to the end. Okay, so this is what I call either the sign problem or the horizontal beam problem. It could be different things. It might not be a beam. It could be a scaffold or a ladder or a 2x4 or a part of a roofing truss or whatever. But the point is, the main focal point, the one object that everything else in the problem connects to is horizontal. So think about it. We've got a wall, we've got a wire, we've got a beam, we've got a sign. Name the object that is touching all the objects. It's the beam, right? What's wrong with the wall? It doesn't touch the sign. What's wrong with the sign? Doesn't touch the wire or the wall, right? Like, do you see how There's other objects, but they might have only one or two interactions in the problem, whereas the central member of this problem, the beam, is horizontal, and it's the central member because it's interacting with all the other objects in the problem. So as part of the setup, you do want to identify what is the central actor, what is the central object, what is the thing that all the objects in the problem are touching. Spoiler alert, I told you I think of it as like the horizontal beam problem. What's the only other kind of problem there can be? Not vertical. Tilted at an angle. Ladders are coming up. Okay, so what do we do now? We want to find, what do they ask us to find? Find the tension. All right, well, okay, they tell us some other thing. They tell us this angle right here, don't they? Okay. They give me some masses, sine beam. They don't give me mass of the wire, so I'll assume the wire is like small enough, or what's that word I can never say? Negligible, thank you, right? So they would have told me the mass of the wire if that was important. Find the tension of the wire. And the force exerted on the wall by the beam, or the other way around. So, all right. We can do this. We know how to draw free body diagrams. We know how to think about forces. We can just go. But I want to give you some tools, tips, tricks of the trade, things that they will go into more detail if you take statics class, engineering statics class, because they'll give you a whole semester of like tips and tricks and methods for working through various situations. What I like to do is I like to imagine that I'm like a bug or an ant or something that's like crawling along my central object, in this case the beam. And I want to walk around the perimeter of the beam. This is something that an engineering professor taught me years ago, and I just think it's absolutely brilliant. Go around the perimeter of the beam. Okay? And as you sort of walk in your imagination around the perimeter of the beam, anytime you come into contact with an object, figure out the forces that are going on there. So let's start at the sine end, okay? Let's say that we're on the top of the beam and we're going to walk to the left, okay? So starting right up there, the upper left corner of this beam, is there anything pushing or pulling at that point? The wire, the tension in the wire, right? Okay, so I'm going to go ahead and go, okay, I know there's a force here, and I'm just going to assume that it's going in the direction, right, that the wire's pulling. Makes sense to me. Okay, and I keep walking around to the left. Am I running into anything? Is there anything attached or any objects like pushing or pulling anywhere along here? No, and then I get to this point. What happened? Now there's a wall, right? And is there a force from the wall on the beam? Yeah. In fact, we definitely know there's like a normal force, right? Okay. So we're going to go ahead and we're just going to, you know what? I'm going to call this W for wall. I know sometimes W is used for weight, but I don't ever use W for weight in this class. So I'll just call that the wall force. You can call it normal force if you want. But normal forces to me tend to point vertically. All right. So there's the wall force. I keep walking around, right? Keep walking around, keep walking around, keep walking around, keep walking around. And then I get to here. And I run into another object, don't I? Okay. What object? The sine. Which way is the sine pushing or pulling on the beam? Down, right? So M, mass of the sine, M sub S, G. MSG! I love MSG. MSG makes things taste yummy. You may have heard that MSG does like bad things to people and should be avoided, all that kind of stuff. That is a racial campaign to smear Asians. You should know this. Those signs that went up on a lot of Asian restaurants in the 60s and 50s, 60s, and 70s were all about white Americans trying to kick the Asian Americans out. And so they concocted this story that MSG was bad for you. Do you know what contains like one of the highest concentrations of MSG? Steak. What's one thing Americans love? Steak, right? Give me my beef, right? So it is what's for dinner. Boy, that was a deep cut from the 80s. So yeah, just watch out. There's no scientific evidence that MSG causes anybody problems. There are, like all chemicals, there are sensitivities. And you can be sensitive to MSG, but it's not going to cause cancer. It's not going to do any of those things. You might have a sensitivity. It might give you a headache, something like that. But otherwise, put it on everything because it makes everything taste yummy. Better than sugar and salt. Yeah. What's wrong with sugar? Dietary advice from Mr. Balogh. What's wrong with sugar? It's a poison. It's a neurotoxin in big enough amounts. Not you'd have to like eat pounds of it a day. Some of you are like, sugar's bad for you in lots of different ways. Okay, we missed something. Well, okay, so there is a tension in that like sine wire right there, but that's just transmitting the force through, right, of the weight of the sine. So good thinking, but we kind of took care of it. No, there's something very obviously that we kind of missed. Gravity, right? This is the one that's pretty easy to miss if you're doing the walking around trick, because the gravitational force isn't like attached, right? Okay. So it's the weight of what that we've missed? The beam itself, right? Now, they just told us it's a horizontal beam. They didn't tell us anything about where its center of mass is. So what do we assume about where its center of mass is? At the center, right? So I'm going to come up here and I'm going to draw a force. This is the weight of the beam. So that's the mass of the beam times g. All right. The skill that I taught you long ago in chapters 5 and 6 of be able to name the object, right, that's causing the force comes into its own here, right? Wanted you to prep you, get you used to that idea back then so that we could then use it now, so it wasn't just brand new and fresh. And so we go around and we ask, like, what's the object that causes MBG? The earth. What's the object that causes MSG? Steak. No, well, yeah, okay, the earth, right? It's the sine, right? What's the object that causes the tension? The wire, right? What's the object that's causing W? The wall, right? We can name objects that are causing those forces. If we have a force on here and we can't name an object that's causing it, we might have made it up. Yeah. Need what? To cause the force? Yeah, so what are the two objects that are causing W? The wall and the beam, right? What are the two objects that are causing the tension? The wire and the beam. What are the two objects that are causing MSG? Sine and the earth, right? Like sine and the beam, okay? So yeah, you always need that. That's Newton's third law. It still holds, right? Okay. So in order for the beam to be in static equilibrium, what has to be true? We need to add up all the forces and make sure they're zero. So we can do that, and then we'll also do the torques here in a second. So like two conditions. So we got an x direction, we got a y direction. We add up all of the torques. They have to be zero, and there's only one torque direction. Okay, dimension. All right, so all of these, it's beautiful. It's like a template. All of these start with 0 equals. Before, they started with ma equals. But now, what is the acceleration? 0, right? So we just start them all with 0 oh my gosh. So if the acceleration is 0, if there's no acceleration, Mr. Balogh, what direction do I call positive? What was the rule of thumb that we had back in dynamics? Which way did you pick for your x and y axes? You followed the direction of the acceleration, right? It's just you did that and you didn't end up with, missing minus signs and that kind of stuff. You ended up with usually fewer components to find. So with no acceleration here, what are you going to do? If there's no acceleration and you're supposed to put your coordinate system in the direction of the acceleration, what does that mean? It doesn't matter. Right? Pick whatever you want. Now, it doesn't matter in that sense, but it supremely matters in one sense. Try to make it so that you don't have to find vector components, right? Like seriously, pick an x and a y axis to minimize the number of vectors you have to go break up into components. Are there vectors in this problem that are like playing nice? That are like lining up in certain directions? Yeah. What directions are those? Horizontal and vertical. Oh my gosh, this is like the best day ever, Mr. Balogh. We're back to that. The right is positive and up is positive. How can this be bad? You'll see. So if I choose my coordinate system like that, what's the only force that I have to go and find components of? The tension. Okay, I want to warn you about something. There is a mistake on the screen, and I made it very deliberately. And so this problem is going to fail on us. I'm telling you that because I don't want to look like a fool in about 5 minutes. Okay? But there is a mistake on the screen. I won't ask anybody if they think they know what it is, but there is a mistake. And by following this problem-solving process, we're going to be able to catch this mistake that this time I have very deliberately made. Okay, so let's go through this. 0 equals, okay. We got to break up the tension. So the tension is going to have a component that goes that way and a component that goes that way, right? At this point, you should be able to identify the directions that these components have to take in order to be added together to make up the force itself. Okay, so we ask ourselves a question. Do we have equilibrium? So in other words, what direction does W point? In the positive direction, right? Positive x, right? What direction does Tx point? Negative x, right? Are those the only two horizontal forces that we have? Sure thing, right? That's it. Is it possible to get 0 from the statement that I've now written down? Yes, right? So this is a check. This is a way to determine whether or not we've considered everything and we're doing it right. If we had W plus Tx, can you add two positive things together and get 0? No, it's not possible, right? If we had negative W, negative Tx, again, that's a problem. We've either written down our description wrong, we got our directions wrong, or if I've got two negative components of force, something's gone wrong. We've missed a force somewhere, we've misidentified a force, something's gone horribly wrong. It's not a guarantee that in writing this down I've gotten everything right. I could still maybe be missing a horizontal force, right? But at least there's the possibility that this could be right? It's like, it's not very obviously wrong. And the same thing goes for the y direction, right? How many forces do we have in the y direction? Oh my gosh. Name one. Ty. And then what's another one? MBG, and then finally MSG. Okay, so I just kind of listed them out. Now, what direction is TY? Positive. MBG? Negative. MSG? Negative. Did we miss any? Sometimes it's like handy to go over and like, I don't know, put check marks on things, right? You do you, but have a method to make sure you can check that. So, is it possible to get 0 from what I have written down right there? I have a positive thing and 2 negative things. The possibility exists that I can get 0, right? If those were all positive or all negative, I'd start to panic. Something is terribly wrong. Okay, that's all fine and dandy. What about the torques? Okay, to be able to talk about torque at all, we have to have an axis of rotation. Now, is this object rotating? No. Is it going to rotate? No. Do we want it to rotate? No. So it's kind of weird to be thinking about an axis of rotation, right? But a torque, they'll call it a moment when you get to statics. A torque needs to be defined from a point, an axis, right, of either possible rotation. It could actually be an axis anywhere in the universe, but usually somewhere on the object itself. So with no indication of where this axis needs to be defined, what does that mean? Where do I pick the axis? Anywhere I want, right? I'm free to pick this axis wherever I want, and as long as I'm consistent with my choice throughout the problem, it's all going to work out. So that's true. You can pick it anywhere you want, but there are some places that are easier than others to choose it. Mathematically speaking, sort of looking ahead, and as one who's done a lot of these problems, I can just give you this piece of wisdom. Always put the axis of rotation at the point of greatest number of unknowns. So on this beam, there are various locations where we have known and unknown forces. What's a force we know in this problem? MSG. What about MBG? Yeah, do we know the wall? No. Do we know the tension? No. So 2 forces we don't know. And the wall over here on the right, left, on the left-hand side, okay, we have just the one force, right? So there's one unknown at this location. And the rule of thumb here is put your axis at the point of greatest number of unknowns. How many unknowns do we have right here? 2. I mean, 1, but there's like 2 components, right? So I would be tempted to put my axis for torque out here. It doesn't matter in terms of getting the physics correct. It matters in terms of making the math easier as we go. And some of you might be saying, but Mr. Balogh, why would you put it there? Tension is what we want to know, right? Why would we put, so what, back up. If I put the axis here, then how much torque does Ty or Tx exert? Answer is really simple. 0. Why is it 0? They're at 0 distance. Remember that torque is R perpendicular to F, or it can be like a really nasty cross product or something, right? But like you need distance, you need a force, and you need distance from the axis of rotation for that torque to be taking place. So if we put the axis right there, then both Tx and Ty have 0 distance, and therefore 0 torque. And it's less torques to have to go and define and figure out. You're like, but Mr. Balogh, those are the unknowns. Those are what we wanted. Yeah, well, where else have our unknowns showed up already? Where else do I have them in my equations? I got them in the x and the y, right? So if I can if I can use this torque equation to find another unknown that I don't want, say the wall force, right? Then I can solve for the tension, right? So like this rule of thumb about pick the location where you have the greatest number of unknowns simplifies the mathematical statement that we're going to have to solve later. That's kind of why we do it, even if it's wiping out things that we might be looking for. Okay. Notice I haven't like written down anything yet, okay? So, because I want to point out something. We're going to choose our axis right here, okay? You need to check the torque. Just like we checked these horizontal and vertical force statements for is it possible to get 0, we want to do exactly the same thing for our torque statement. Even before we write anything down, we want to make sure that if we choose an axis here, that we can get 0 torque. What do I mean by that? Well, use your pencil. I showed you this trick before, right? If you hold your pencil like it's the beam, right? And you hold the end, right? Where we're going to put our axis. So this would be like the wall right here, right? And I'm holding the point, my axis point right here, okay? So Ty, Tx, MSG, those are causing no torque, right? So the only other two forces we have to check are the wall force and MBG. Well, what's the wall force going to do? Is it going to cause a torque? No, why not? It's not perpendicular, right? There's no part of W that's like perpendicular, right, to the distance along the beam, right? Okay, well that leaves MSG, doesn't it? So what do you do to figure out the direction of torque for MSG? Pull down. So does the beam rotate? It's rotating in the counterclockwise direction. Is that right for you guys? Okay, so counterclockwise direction. Okay, so we have a counterclockwise torque from MSG. What must we have in order to get the torques to be 0? A clockwise torque from somewhere else.
Would it be MBG that's causing the torque?
Sorry, I meant MBG. It's the beam's weight. MSG's over here at 0, right? Not causing any torque. So the wall not doing anything, MBG pulling this thing down, causing it to rotate counterclockwise. Where's the other torque? Tension 0. What do we know right now? It's not the wrong spot. Because no matter where I put an axis, if this thing's in equilibrium, the torque should add up to 0. I have an unbalanced torque. I have a torque that's only pulling it counterclockwise. I need some sort of clockwise torque. Do I have any other forces that can be causing torques?
Would it be friction on the wall and the beam?
This is the mistake. We've painted ourselves into a corner here. In choosing the axis out here, and it should add up to 0 if we've done everything right. It's not adding up to 0. Let's practice this using a different point. Let's say, let's choose the axis point right here at the wall. Okay? So if we choose the wall, right, we hold it at the other end. MBG causes a torque in which direction? Clockwise or counterclockwise? Clockwise, right? Okay. MSG. Clockwise, pulls it down, right? TY? Oh, wait a second. So we have clockwise torques and we have counterclockwise torques, right? Is it possible to get 0 torque? Yes, because we have both directions represented, right? Oh, so let's just do the problem from that end. We need static equilibrium no matter where the axis is. What's another place we could pick the axis? Center, right there, okay? So now, is MBG causing any torque? It's 0 distance, right? Okay, so over here at the wall, does the wall cause any torque? No. Does MSG cause a torque? Yes, right? Does TY cause a torque? Ooh, are those in opposition? So that's possible there, right? But as soon as we come to this location, it all falls apart, doesn't it? And you be tempted to go, well, just don't think about that spot, Mr. Balogh, right? That's easy. No. Static equilibrium needs to be true everywhere, all the time, for any axis you choose. This is why when you're setting up the problem, you want to check at least 2, if not more, points on your object, your central member. Pick an axis and just do a real quick conceptual, okay, can I get 0 torque here, right? In the case of grabbing it at the end where the wire is, all I've got is MBG, which is telling me that we have missed something. And this is the mistake I alluded to earlier. There's a missing, we made an error on this diagram. Does anybody think maybe they've caught it? The wall force isn't just a normal force coming away from it. If I had this ruler, right, and I attached it to the wall, right, and I hung something off this end and I put a wire up there, right, if this side is frictionless, there'll be a normal force coming off, right? But what will this end do? It'll just slip right out, right? So there needs to be friction here, or even better, there needs to be like a pin or maybe a support block or something, right? That's providing a component of force upwards. And how do I know it needs to be a component of force upwards? Whoops. So I'm going to call this wall Y. I'm going to call this one wall X. So wall X. So how do I know it needs to go upwards? Well, take a look at the torques. If we're at the end where the wire is, MBG causes a counterclockwise torque, doesn't it? What direction do I need over here at the wall to counter that? An upwards pointing force that causes it to go clockwise. You're going to find that as you apply sum of forces equals 0, sum of torques equals 0, that you might get to points where you see, wait a second, I'm unbalanced. I don't have anything to counter this. That is a warning, right? That's a symbol or a sign that something is missing, something has gone wrong. What I tend to do is if I've got an interaction like where the beam meets the wall or where the wire meets the beam or something like that, I tend to draw components there automatically, right? I might find later that one of those components goes to 0, like it's not necessary or something like that. In statics, they'll teach you several rules. Like, for example, one of those rules is, and I didn't tell you here, but if like there's let's do an exploded view here. If here's the wall, here's the beam, right? And like, let's say that there's like a pin structure right here. There's there's a hole in the beam. Oh, I got holes in my beam right here, right? If this is up against the wall, there's a hole right here. And I can slide a bolt through that hole and it's being held up by a bracket, okay? In statics, they'll teach you that if you have a pin, and a pin is what's allowing like the articulation of the structure, then you will automatically assume that there are 2 forces here. It's like guaranteed that there's going to be 2 forces there, okay? For other types of couplers that they have, they'll teach you other rules. The statics book I have has a table of like 15 or 20 things in it, right? So, but anyway, that's getting maybe more into the nitty-gritty than we need to do in this class. So for our purposes, for this class, for a single chapter, right, it just sometimes go through and do the due diligence, right, of figuring out the torques on your object. Notice I haven't written down any torque equations or anything, right? This has all been concept. It's all the idea of can I get 0? And I'm going to check a couple of axes. Okay, well, now that I've checked and now that I see I've got like way more unknowns, like I've got a WY and a WX that are both unknown, right? And I've got a tension Y and a tension X. I've got 2 points on my beam now that have the same number of unknowns in them. Where do I put my axis? My actual axis that I'll actually write down and use. Remember, the rule of thumb is pointed at the greatest number of unknowns. Doesn't matter. You can do it on either end of the beam. Don't do it in the middle, because there's a known thing there, right? Do it at either end. I personally would tend to go for the wall, seeing that the wall now qualifies as a point of greatest number of unknowns. I like to draw an X. I like to label it as axis, so I can come back later and go, okay, what the heck did I do? The reason I kind of like to do it there is I don't know, in sort of my imagination, if the wire breaks or isn't strong enough, the whole structure will kind of rotate where it's attached to the wall, right?
Again, what was going to be the two forces if we're putting it together?
Right over here. If we put our axis here, then this causes a torque, and this one causes a torque in the opposite direction. It was this WY that was missing. It's going to turn out to be friction, but yeah. We've been going for 50 minutes. How much of this problem have we gotten done? We haven't even gotten into the math part yet, right? We are just on setup. Guess what you get to do in statics class? No, like you'll have days where there will days of lecture where you are covering one problem. Anybody want to change their major? Physics statics is easier. Counselors are standing by. I'm trying to get you guys to be physicists. It is cool to understand everything, right? It's kind of fun. All right. And engineers make it real. Physicists, we don't do anything real. We stay away from real. All right. So now that I've got my axis defined, now that I've gone through all of that, the other thing I need to pick is a direction for positive torque. Does what you pick matter? Yes, but no. Does the direction of positive matter? No, it can be whatever you want. Clockwise or counterclockwise. What do you want? Clockwise? All right. So we're going to pick clockwise direction as positive. The only thing that matters after this is that you stick with your choice, right? Just like we stick with our choices for X and Y, we stick with our choices for positive torque. Okay, when we write down torques, we just identify the torques that we have. There's a torque from MBG. There's a torque from MSG. There's a torque from TY. And I suppose we could write down torque from TX. But what do we know about the torque from TX? That force right there against this axis right here. Is there any part of TX that is perpendicular to the beam? No. So what's the torque from TX going to be? 0. Okay. So I wrote down that I had these torques, that these are the things that can cause torque. Now I go through, what's the second step? We did this last chapter. Signs. Okay, MBG, positive or negative torque? That didn't sound very sure. Okay, so how do you check? You hold your pencil, you hold your pencil like the beam, you hold the end where your axis is, and then you apply the force. We're talking about MBG, so we're going to pull down. Which way does the pencil go? Clockwise, right? What did we say clockwise was? Okay, now we do it with MSG. Which way did it go? Now we do it with TY. Okay? Just to summarize, when you write these down, you're going to check that you can get 0. And that check's pretty straightforward. Do you have positive and negative things? Yes, or right? If they're all positive, there's a problem. If they're all negative, there's a problem. For the torques, it's harder. For the torques, not only do you say, okay, can I get 0? Yes, in this case, I've got 1 negative and 2 positive, so it's possible to get 0. you have to check multiple axis definition locations. I tend to pick one and then pick the other end of the object just to see, right? Generally, I can catch all my mistakes if I do that. So that one requires, the torque one requires more heavy lifting. All right, we're not quite done with writing down these torques yet, because I need to define this as a distance times a perpendicular force. So, what's the distance to MBG? What distance am I talking about? Where does the distance start? At the axis. This is the point we've defined we're going to measure everything from. And it's the distance to where MBG is applying its force, right? A distance perpendicular to my force, right? So, what's the distance? Half the length of the beam, whatever it is. They didn't tell me what the length of the beam was, right? Times the force. What's the force? M sub B times G. All right. What's the distance to MSG? It's the length of the beam. And what's the force? MSG. M sub SG. Minus. And then TY. What's the distance to TY? It's the length of the beam. And what's the force? TY. 56 minutes. And that's with my help. I wanted to lay out for you a process. Let's go over the process. First step, what do? Diagram, right? Get a picture down. You're drawing a free body diagram of a situation. Hopefully, maybe they provided a picture for you. Second thing, identify the central member, the thing that connects all the things. And there could be multiple of these. I try not to give you any problems like that, but you'll be up against them in statics class, right? But in this case, the central member was the beam. Third, write down sum of forces equals 0, sum of torques equals 0. Now, this is a big step because there's lots of things you need to do in there, right? You need to define axes for the forces. You need to identify all of the forces, things that are interacting. You're going to use Newton's third law to help you, right? What object is causing this force? You're going to walk around the perimeter. You're going to remember gravity. There's lots of things to remember in this step, right? But you're applying sum of the forces equals 0, and then you move to sum of the torques equals 0. Define an axis, and once you've picked an axis, pick another one and check it too. Conceptually, you don't have to do the math, but check to make sure that you can get 0 torque out of the diagram that you have. Write down your equations, and once you've done all that, and that's the only part we've done visualize and strategize. Our strategy was getting all of this down, right? What's the third step? Do it. What the heck are we doing? What do they want? Tension in the wire and force on the wall by the beam. Now it's a math problem. You know how much I enjoy doing math. So what have I got? I've got this equation, I've got this equation, and I've got this. I've got 3 equations, right?
Should we add the WY to the sum of forces on the y direction?
Oh yeah, we do. Thank you. Because it was a mistake and we had to go in there and do this, didn't we? Thank you. I would have gotten there in the end because I would have been like, what happened to my WY? Okay. So, first thing I'm noticing, there was an L in every term, wasn't there? Okay. That's nice. And then I can move TY over to this side. It's negative, and so when I move it over to the other side, what happens to it? It becomes a positive. TY Now what am I left with? 1/2 mass of the beam times g plus mass of the sign times g. What do I now know? I know Ty. Turns out that this is 490 newtons when I put everything into my calculator. Okay, I now know Ty. Is there anything I can do with Ty? It's sitting up here, right? And so that's a number, and this is a number. How am I going to sign the thing I don't want? Algebra. So Wy, I got to be 98 newtons. Well, that leaves Wx and Tx. How am I going to find those? Trig? Ty is equal to T sine theta. Why is it sine theta? It's not touching the angle, right? So can I find T? The tension? Why would I want tension? Well, because Tx is equal to T cosine theta, isn't it? Boom. Now I have Tx. Tx turns out to be, the tension turns out to be 855 newtons. And then Tx turns out to be 700 newtons, which means Wx is 700 newtons because Wx and Tx are equal to each other. And so what have I found? I found the tension in the wire. Better put a square around that one, right? Tension in the wire, 855 newtons. Why would I want to know that? Why is that important? If you're going to hang this sign and you need to pick the right kind of wire to use, what are you going to make sure the maximum tension the wire is going to support is definitely going to be? Bigger than that. If you're a smart engineer, you double it. I'm a terrible engineer. I quadruple everything. Like all the shelves in my house, I can hang elephants, small cars off of them, right? All my wife wanted to do was put books on it. I was like, we're going straight into the studs on this one, right? So, yeah, I'm a terrible engineer. I don't know. Oh, well, I know Wx and I know Wy now, don't I? But that doesn't tell me what the force on the wall is. Again, important information to know if we want to pick a material that's not going to exceed, right? So how do I find the wall force? Is it Wy? No. Is it Wx? No. What is it? It's both. But they're vector components. So how do you find it's the result. So it's Wx squared plus Wy squared. This would be the full force that's in the wall, which turns out to be 707 newtons. And for those of you who are curious, at 8 degrees. Okay? So math happens, and a lot of math can happen, but before all that math can happen, which I did very quickly, there is a lot of setup and thinking and application of concepts and ideas and using of torque and all that kind of stuff. You know it's a really, really bad day in physics when most of the class has just been one example, right? So I'm going to leave you with this one. Again, on purpose, I haven't given you a picture. Okay? I do want to point out for that class that did see me snap a ruler across my knee, I found a meter stick, right? That has centimeters and millimeters and 1 meter on this side. All right. So, picture in our heads. I brought a ladder. Okay? So, this ladder has weight. And what does they say about the ladder? What's it doing? It's laying up against the wall. We'll go this wall. Okay? So it's kind of like leaning like that, right? Okay? Now, they told us something about the vertical surface here. It's frictionless. Don't put your ladder on a frictionless surface. Just don't, okay? I'm putting this one on glass. This is plastic against glass, so this is pretty frictionless, right? Okay, right? And now, what does the painter do? Poor choices. What keeps me safe? It's the friction down here, isn't it? Is there friction down here? There better be, because if the floor were frictionless, what would this ladder do? Right? Okay? So, important safety tips when we're using a ladder. Don't do ladders like this. Right? Why? You know that it's going to slip out, right? Okay? But we're going to find out why. We're not going to do it today. But we're going to eventually, Thursday, we're going to find out why this is, okay? That the safe thing to do is to have ladders be as nearly vertical as you can get them. Now, you don't want to make them so vertical that as you start climbing, you do this, right? Okay? Because there can be torque in the wrong direction if you're not careful, right? You do want there to be enough of an incline so that as you come up, right, this wall has to support it out, right? But the thing that keeps me safe is the friction down here. Now, if you're on like a really big extension ladder, and ideally you're working with somebody else, buddy system keeps you safe, right? Okay. The person at the ground holding the ladder, a lot of people just grab the ladder to hold it. Okay, that's fine. You've steadied it a little bit, but what's the more important thing you should do? You should put your foot up against the bottom of the ladder where it touches the ground to keep it from going this way, right? That way, your buddy falls off the ladder, this is their problem, okay? You made sure the ladder wasn't going anywhere, okay? Don't catch them. I mean, you can try to break their fall. Better to push them into a bush or something like that. Because if you end up being the target, then there's two people that are hurt, okay? One of you needs to be able to call 911, so make sure it's somebody. Okay. Looking forward. You are going to have a problem that looks like this, okay? You already have post-traumatic stress disorder associated with penguins. You will now have the same for ladders, okay? Because this is a. When is chapter 12 due? Is it this Saturday? Yes. Get all of the horizontal problems done now. Okay? Try to get those done as soon as you can. Because the ladder problems, anything that's tilted at an angle, it's going to wreck your brain. And we'll wreck your brain more on, Thursday. Tomorrow, there will be time for you to get started on chapter 12 homework. Take advantage of it. After you do the exam autopsy, plan on staying to get help on chapter 12 homework.